Shadaydeh. My colleagues, Andrea Manukovac and Tamar Sirani, are within the image processing group in the Institute of Computer Sciences and Control, Hungarian Academy of Science. My talk today will be about the change detection in wetlands using multi-layer fusion Markov random field. Here's the outline of my presentation. After the objective, I will introduce our multi-layer fusion Markov random field model for change detection in remote sensing images. And in this model, we in particular use a specific feature which is related to the similarity between different image layers. So I'll introduce briefly on the improved local similarity measure algorithm, and then I will show some experimental results and conclude my presentation. So as we know, it's very important to monitor the land use changes to understand the natural as well as the human-made environments. So our purpose was to develop a an algorithm or cross-classification comparison model for detecting region of changes in remote sensing images that come from different modalities or different sensors or different weather conditions. What we mean by cross-classification comparison is that in our model we first classify the different layer of images and for various land cover classes like urban areas, wetlands, forests, or different vegetation classes, and then we compare these classes in different layers to detect changes. In this slide you can see the workflow of the proposed model. We have as input three or could be more, 2, 3 or could be more images, and these images are from different sensors, different modalities, and for each pixel in the image for each pixel in these images, we create a feature vector that describes the pixel. This feature vector might be spectral features, spatial features, or some statistical measures. And we create this stack of features of the different layers. We perform clustering on this stack of feature vectors, and the result of the clustering is used in the Markov fused segmentation of the 3 layers using Markov random field. The result, class map of this stage is used as training initial parameters for the segmentation of each single layer separately. And after this segmentation, we can get the class map for each image. And here we use simple example, just vegetation and meadow, 2 classes. And comparing this class maps, we can detect the changes between each 2 images. Here's the change in white. Here you can see correspond to the change between this area and this area, while the forest cut change here, this difference between these 2 images shown here is the forest cut you can see here, while it is here as forest. Now, as I mentioned before in the previous model, in particular we use this what we call local similarity between 2 images. At each pixel we calculate the local similarity between each 2 pair of images. And because we are dealing with multimodal images, we cannot use local similarity based on intensity values. We choose to work with the statistical similarity measures. In particular, we choose to use with what is called cluster reward algorithm, and it's basically calculated from the joint histogram of the 2 windows or corresponding windows in the 2 images. And the problem here is the choice of the window. If we choose a small window, we will have large estimation error in the local similarity measure. If we choose to work with a large window, we will have better estimation, but we will lose small changes in the images. So in order to solve this problem, we developed a new algorithm for the calculation of the similarity measure, which by itself can stand alone as a change detection algorithm. The idea is very simple but very effective. Usually when we calculate the histogram or the joint histogram, at each pin or each intensity value pin, we calculate the number of pixels this intensity pair ij occurs. However, we said that we will not calculate the histogram as the number of the intensity values, but rather by the summation of the weights we give to each pixel in the image. So we give each pixel in the different reference image a weight, and the histogram is calculated as the summation of these weights. Now the weights, without going too much mathematical details, is basically decided by how much the pixel is far from the center of the window, and how much this pixel, when compared to the other image pixel, shows more change in variance. Here's also an example. If we want to detect these changes between these two images, and here is the result using the conventional histogram or similarity measure. Here is the result using our improved similarity measure estimation. As you can see, the forest cut here is much better detected using the weighted histogram. Even for the changes here, also this reflects much better results. As for experimental results, I'll show some different experiments using different types of images. In the first experiments, the focus is to segmentation of land cover, and it was supervised, which means that we used some training areas for the clustering process. We used 3 multimodal aerial images. We have 3 components, RGB, and it's for the area around the Tisa River in Hungary. The spatial resolution for the image was 0.5 meter per pixel. In this experiment, we used mainly the local similarity measure and the luminance value of the LAB color space. Here is the result of, this is the original image, and this is the areas for different class training. We have sound, forest, river, and meadow. And here I show the result for different methods. In the first and second row, you can see the result for the conventional single layer Markov random field. Here with single layer Markov random field, but with the similarity measure. And here's the multi-layer fusion Markov random field we introduced, but without the use of similarity measure, here with the similarity measure. The important point here is that the part of the river here which has dense vegetation shows as a forest or vegetation class in these 3 methods, while we could here detect this part of the river as water correctly using the similarity measure, And to compare the result, here you can see the infrared image, and here's the result in case we use the infrared image. So what we could get here without the infrared is similar, with the help of the similarity measure, is similar to what we could get with the help of the infrared image. In the second experiment, the purpose was to monitor reeds in wetlands. As you know, reeds is a very important species for maintaining the health of the wetlands. And in this experiment, we had two multispectral RGB and the near-infrared channel for two layers images of the Keszthely area in Hungary. We have two images from 2012 and 2015. The spatial resolution is 2 meters per pixel. In this experiment, we used unsupervised clustering first, and then as feature vectors, we use the NDVI values for two layers and the near-infrared channel and the luminance component. Here's the results. This is the image for 2012 and this is for 2015. And here's the read class shows in light blue for the 2 years. And here's the grounded truth provided by Dr. Zelinsky on site in 2002 actually. And in this image we show the change in the read class, where we could detect whether it's new read or it is deteriorated read. I mean, for example, you can see the area here. You can find some changes corresponding to the blue changes here. In the third experiment, we applied the proposed model to Landsat RGB images. We have only the RGB images of Barana River in Paraguay, which is the second largest river in South America. We have images from available online on the internet from on years 1985, 99, and 2010. And the purpose was to monitor the effect of the dam, which started in 1983, but didn't go to work until the 1993 actually. So the image at 1985 is the situation of the river before the dam effect starts. In this experiment, we use the RGB color value directly in the fusion Markov random field for 3 images. Here's the results of the fusion Markov random field segmentation to 3 classes, and this shows the changes between this here. This is between here and here, and this image shows the changes between these 2 days, which shows the big influence of the dam on the river between 1985 and 1999. So to conclude my presentation, we have proposed a multi-layer fusion Markov random field model, and we use this in the classification and change detection of wetlands in remote sensing image series. The advantage of our model is that we can use different spectral or spatial or statistical feature, and based on the application. For different application, we can use different features. And for example, the use of cross-layer similarity measure helps to better identify some classes where radiometric values are dubious, like in experiment 1, while the fusion of 2 layers of the normalized difference vegetation index result in considerable improvement in the read classification. Now, another advantage is that since the outcome classes of the multi-layer segmentation is later used in the training of each single layer, similar classes are automatically given similar labels, which means that not only we can detect change, but we can also define the type of change that took place. So, thank you, that's all.